Hey, where's your brain book at that I gave you information and everything, and it's got the data sheets? So I'm going to show you guys the big bugaboo secret of the knife making business. All right, here we go. Every steel that we use, I've written down a recipe for and a procedure for heat treating it. I've written the recipe and how I want it out of the computer. Everyone says, oh my God, you must be a metallurgist to come up with all of that. Not so. What I have here is a crucible data sheet. This is where my crucible steel comes from, and these are the guys who make it. And they tell you exactly how to heat treat, anneal, draw, to stress relieve and temper your steel. I've been on the phone with these guys directly. There is no hand-me-down secret magic to this. Heat treating is a science. It's like, I'm going to tell you, it's as easy as baking a cake. All you have to do is have really good data, have really good instructions, and know exactly what steel you're working with, and know how to measure your temperatures really well. Other than that, it's quite simple. I want to talk just for a minute about why we do our heat treating in-house as opposed to sending it out. You will hear that the only way you can get a good heat treat out of modern steel is in a vacuum or a thermal control. It's not true at all. There's lots of excuses for why you should or may want to choose to send out your metal for heat treat. And most of them aren't valid. We Inconel bag all of our stuff. So if you look over here, everything that goes through heat treating here, it gets put into a Inconel bag. It gets labeled what it is, what type of metal it is, and it gets heat treated in here. You use a little bit of stoichiometry and you know how much carbon to put inside to burn up the oxygen in the bag. And as it comes through 900 degrees Fahrenheit, it burns up that oxygen and you don't carburize your blades. Your blades come out a nice even gray color, and from there you can finish up your knife. If your blades coke up, carburize, scale, and get nasty looking, it makes a lot of extra work for you. That being the case, if you get your knives very close to done in the soft condition, you're going to want to use a vacuum. You'll send them out and they'll have a furnace, big furnace like this, and it sucks a vacuum and pulls most of the atmosphere out, and then it runs up the temperature and runs a heat cycle. But here's the problem, and I've had heat treat facilities bristle with me about this, but the competitors will say it's true. A big production heat treat oven doesn't hold, in my experience, a tight enough heat consistency from top to bottom to guarantee you a perfect heat treat. And the reason why is because they don't have temperature gauges every 6 inches front and back, and because a space that big is hard to control the temperature. So what you get, the more exotic steels have a tighter and tighter band for their high performance heat treat. They have a tighter and tighter band that works well of acceptable temperature. It's not like, oh, you heat it up till it's orange and then you quench it for 9 seconds in oil and then submerge it till it's cool, and when your hand can touch it, you put it on dry ice. It's not like that. It's very, very exacting. Most knife makers, which is all but maybe 5, they can't send enough knives to a heat treat facility to fill up the whole oven. So you get part of the oven and it gets crossed over with other stuff in the oven. And you're either in the hot spot or the cold spot, or the spot that's just right. And that's about the percentage of how much come back within spec when I test them. I've sent blades out to a lot of places, and I find about a third of them pass the hardness that I advertise. A third. A third are close, and a third are not even close. So what I found was, I do it all in-house. Every single blade gets hardness tested. Every single blade has 3 opportunities for us to QC the hardness. Every single blade we get to see if there's been an anomaly in the process at least 3 times, and then we get to draw it exactly to the hardness we want every single time. Very few exceptions to that. We've got, this is the brainchild of heat treat right here. This tells you everything you need to know to heat treat 4 different types of metal. And then what we do, we have a process that's made around grinding off the outer molecules of the steel after we're done heat treating it. So anything that could have any surface irregularities because of not being in a perfect vacuum, the first thing we do is surface grind that steel away. So we're now one layer inside the original heat treated item. We're a layer inside of that metal. And then we finish grind, and then we soften and edge grind, which means every part of the metal that comes out gray that could carburize in any way, shape, or form is removed from the knife, unless you get a Vulcan finish knife from us. So that's all done here in a few steps. So the Inconel bags, once the knives are bagged in there, they come into one of the 3 ovens. These will usually be set in the afternoon. They'll pop early in the morning on a timer. And about the time we get in, Brandon will have to start watching and looking for them to see when they're ready to come out of the machine. Right now, he's prepping bags. He's dropping the right amount of carbon inside the bag so it burns up the oxygen. And he's getting them all ready for the next batch of heat treat. They'll run through their cycle. So they'll heat up about 1700 degrees. They'll normalize there at 1700, and then they'll ramp up at a very calculated rate to whatever their critical temperatures are, whether it's 1925 or 1850, our 2 primary temperatures we use in heat treat. If you heat treat towards the top and low band of the spectrum, you can get different outcomes. So we play with that while we're heat treating, and that's part of our recipe. Once they come out, they get yanked out. If you look in here, it's a full bag of ripped up Inconel. So once they come out, he'll slide this table down in front, pull the blades out kind of fast and furious, and he'll plate quench them between these 3/4 inch plates of aluminum. They'll get plate quenched so they drop from their critical temperature down to a kind of reasonable temperature that won't burn you to death. Then as they come out, they're still really hot, like too hot to touch. Every single blade is hand straightened. So every single blade will come over to here, and he'll hold it to this straight edge up to the light, and then he'll adjust by hand. Up to the light, adjust by hand. On every single blade, every single one is being straightened by hand, and it's done a couple of times throughout the cooling process. They really thermally stabilize after about 300 degrees Fahrenheit, and then they become, when they get to room temperature, you can't move them. But when they're a little too hot to touch, say 150 to 300 degrees, you can bend these 1/4 inch thick blades, just bend them by hand and straighten them out. So usually they're quite straight because we plate quench them, but once you got them all in the cooling rack here, we stand them all up, we got a fan blowing across them. If they're off a little bit, they cool on one side more than the other, they'll pucker that direction. So it really is kind of a juggle at the end. It's like the Ed Sullivan show, rotating plates on the end of a stick. You gotta get them straight, and you gotta kind of keep checking them. And when they stop burning your gloves, you're like, okay, these are cool enough, they're stable. And then while they're still too hot to touch, we're waiting for them to get somewhere around 130 degrees or so. We start the draw on them. You've changed the carbon from austenite to a martensite form. And if you have any retained austenite, there's a little trick for getting rid of that. But if you've done your job right, you bring it up to this critical temperature and then you slam it in the quench. You plate quench it and let it finish cooling in the air, and its hardness goes way up. So we get stuff regularly close to, on the Rockwell C-Scale 70, which is ridiculously hard. It's too hard for a knife, it's too brittle, and it's too hard to sharpen. So we like to draw everything back down. If it's D2, we like to draw it down to around 60 plus or minus 1. If it's S35VN, we like to bring it down to 59 or 58.5 plus or minus 1. Every single blade, every time, and it's a science. It's just follow the recipe. I've come up with the recipe by consulting the engineering paperwork and talking with the engineers who make this steel, and then I've put together these very specific recipes, and then my guys follow the recipe. The real skill is in keeping them all straight and not letting them ever stabilize. So we heat them up, we slam them down, and right about the time they start to settle down, we warm them up again a little bit, and that relaxes the steel. Because when you take that carbon and you transform it to this martensitic structure, the blade becomes very rigid, and you want to relax or you want to temper it. You want to calm it down a little bit So we warm it back up, and that is where we can dial in our hardness exactly. So people ask, well, how hard do you make your blades? Well, the truth is we all make them the same kind of hardness. When we make them, the answer, as hard as we can. And then where do we draw their hardness down and temper them to? We draw them to where the performance spec in the recipe says it will be toughest and have the best stain resistance. So we draw them back down. It's based on science. It's not like Greg's opinion. So based on the chemists who came up with the steel and the company that spent millions of dollars in their test equipment verifying and coming up with their data sheets, we build a recipe around their data sheets and we do not deviate from it. And it works really, really consistently, really, really well. And no commercial heat treat house will follow and come up with these individual recipes because it's not profitable. They want to batch you all into a big batch and run a full oven because they make their money off cycles. We make our money off everyone being right. So if you're a knife maker calling bullshit on me, I'm willing to go head to head and attest anytime, anywhere, anybody on the planet with heat treating. With the final results and true testing. I'm always willing to put my money where my mouth is. What I'm talking about, this is my way that I've come up with, and it casts all hearsay to the side. It is science, it is a recipe, and we follow it. And if it's done right, you'll get years and years of wonderful use. And if it's done wrong, it's a nightmare and you can ruin your reputation. I've heard a lot of old-time knife makers say, the ideal steel is less important as a perfect heat treat. Less important than a perfect heat treat. And I believe that in some regard, but we try to use the best steel also. So we run our recipes here, we do our hardening here, we do our drawing down or tempering. When you say, oh, what do you guys temper your blades to? Well, we heat treat them and harden them to as hard as we can, and then we temper them or draw their hardness out of them with heat. So if the more heat you use, the softer you make them. So we have found a number based on reading a chart and coming up with a recipe and reading performance specifications and some testing ourselves to come up with the ideal hardness that we like. When we've done that, then we cryogenically soak them. It's a hell of a process, but we're able to control our hardness exceedingly well and repeat it very predictably, regardless of what exotic steels we're using. These small ovens, you're able to tell when the temperature's not working properly, and you're able to control the temperature really well because it's so confined. I think that about covers heat treat. You know, the last thing I'll tell you if you poke your nose over here is every blade during the heat treating process will sit in alcohol at some point with dry ice, and that's where we try to transform any retained austenite that's left after the quench. So all has to be done in a certain time period after the heat treat. And then we hardness test here while everything's still warm, and we monitor how the blade is changing throughout the process. And what you get is, if you look on a graph, what you'll see is this hardening, this softening in a couple stages, this freezing, and then you get this really stable number at the end. That's how we do our heat treat process. We do it time and time again, every single day, re-verify, time and time again, calibrate, verify, check, follow the recipe, and that's how we get the results we do. And then a craftsman's got to be there, massaging them straight as they cool, keeping track of every little thing, and balancing out all of these forces that we're contending with to come up with the right heat treat.